This video was brought to you by AnyDesk.
This is a brass-sintered purge, and according to the available information online, it's a metal porous diffuser that helps distribute jet-like gas flow evenly across a volume. It basically stops your air compressor from making this noise. I'm laying on the floor because the air compressor is under the table. I'm not trying to look sexy or anything. Now, I didn't buy this because I want to avoid the magical sound of my air compressor relieving itself. I actually enjoy it. I bought this because, as it turns out, this works really well as a combustor.
I recently built a tiny rocket engine made out of brass water connectors, and it worked better than I expected. The reason why it works so well comes down to the fact that I studied a small camping stove I have, and I realized the secret for good combustion is slowing down the flow of gas, or in other words, diffusing it. To achieve this, I drilled many tiny holes on a 1/2 of an inch plug, so the gas would spread out evenly into the combustion chamber. But trust me when I tell you, drilling tiny holes is not easy. You see, normally when I design a rocket engine, I first calculate the mass flow of gas and air I need to get a very nice amount of combustion. To do that, I normally need to know the pressure of the propane and the pressure of the air, so I can calculate the dimensions of the holes for the injector, being those holes the tiny holes I mentioned before.
The problem is, the holes on this part are already made, and they're microscopic. So how on earth am I supposed to, measure them? I could give it a try, but I think I have a better idea.
Building rockets, it's all about designing holes. Holes for the inlet, holes for the injector, and the most important hole of them all, the nozzle. The reason why you need to do math to get the right dimensions for the nozzle is pretty straightforward. Once you build it, that's it. That's the dimension you're getting. It's set in stone, or in most cases, in metal. You can't change it.
What if you could? You know what would be fun? To do things the other way around. I use this as the injector, I ignore the math, which, if I'm being honest, I normally do, and I build an adjustable nozzle I can adjust until I get the desired results. Sounds like a dumb idea? Well, you clicked on it, and I'm building it. So, this is a modified iris mechanism. You normally see it in camera lenses. It's used to adjust the size of the diaphragm. And if I remove this lid here, you can see it's actually very simple. It's just a bunch of slide-in triangles. But you can also see that I can't really adjust the size of the hole by much, especially if you compare it to the overall size of the mechanism. Okay, I spent the last hours redesigning the mechanism, and now it opens a little bit more. I didn't do much. I just cut the corners of the triangles and tilted them a little bit. My main concern now is precision, because PLA is not very precise, and this mechanism by default needs to be precise. The triangles need to slide very close to each other with no gaps. So what I'm gonna do is 3D print this design in my Form 4 resin printer. They have a resin called precision resin, so it's in the name. But right now I'm washing the parts with alcohol. I normally use isopropyl alcohol, but I'm out of it, so I had to use 99% ethanol. It works pretty well, but now my entire shop smells like vodka. To be fair though, my shop has seen worse, or smelled worse. Oh, come on! I'm trying to look professional. There you go. Okay, look at that difference. Now let's give it a try. Not too bad. But it's not fully opening, and I'm guessing it's because of friction. I think I'm gonna use some graphite to lubricate this. Okay, as you can see, I put some graphite on the parts to lubricate them, and when I put the lid on, now I can close it and open it much more smoothly. The problem is, when I try to open it completely, I hear a click. And what's happening is, the parts are tilting and getting locked in place, which is not good. I think it's because the grooves of the lid that are pushing the pins are straight. And because of that, when it reaches the limit, it pushes it at an odd angle and tries to push it in the other direction. That's why they're tilting. So in the next iteration, I need to make the grooves a little bit curved. The only reason I'm testing this with compressed air is to make sure this won't disintegrate once I give it pressure. That and I want to hear my compressor sighing. It's leaking through the thread, but I guess that's good enough for now, right? I need to do the combustion version. So because the graphite works so well to lubricate the parts, I guess I'm gonna make the entire thing out of graphite.
Graphite is a great material. It's easy to machine, it can withstand up to 3000 degrees Celsius, which is very useful when you consider I'm trying to make a rocket nozzle, and it's low friction.
Crap! That's still hot! Oh, that's gonna leave a mark.
Its only fault besides burning idiots is being very brittle and getting everywhere when I machine it. It turns into a very fine powder that gets everywhere, on my machine, on my cameras, my hands and face, and on my floor. It's also not easy to clean off. The only thing that seems to work is sodium hydroxide.
As you can imagine, I don't use sodium hydroxide to clean my face, because that would be stupid and dangerous. And that is not what this channel is about. This channel is about rockets, science, engineering, a slight distaste for tomatoes, and most important of all, learning.
Sponsor time.
So, the sponsor for this video is AnyDesk, and normally what I would do in this kind of ad is talk about their software, and how amazing it is, and how many features it has, but that's not what they asked me to do. What they asked me to do was to ask you for a video idea. A crazy expensive and ambitious video idea that I'll build and they'll pay for. I know, I was also surprised. Apparently the AnyDesk team also really likes science and engineering, so I'm guessing they just want to help makers make, you know, cool and exciting projects. So I'm counting on you. Give me your best ideas. There's a link in the description, anydesk.com/science. You can use it to submit your idea. I'm actually very curious to see what's coming out of this. I hope it's big, cool, and has combustion. A big shout out to AnyDesk. I've been doing YouTube for a while, and I have to tell you, this is a first. If you're curious, their software is used to remotely control other devices. For example, I can be on the other side of the world and 3D print a part on my 3D printer without ever touching it. It's pretty cool. Also, you can download it for free. But like I said before, you don't have to. You just need to submit an idea. A big thanks to AnyDesk for sponsoring this video. And now, let's get moving. Okay. Now comes my favorite part of the project, which is adding propane to the mix to get combustion. Normally I need to heat up the propane can in some shady way so I can get a raising pressure, but because we're in the middle of summer right now, I don't need to do that. It's super hot. I got my pressure. So let's proceed. So as you can see, my graphite nozzle is completely unfazed. I mean, not even a scratch. But I try this with a nozzle fully open, which normally is easier to ignite. Let's try to close it a little bit and give it another go. Yep, I thought so. Okay, so what's happening is, even though it's hot, when I open the can to test the engine, the gas decompresses and gets colder, so the pressure drops. So I guess I'm gonna need that shady way of heating up the can after all. Very good. It seems we have our 4 bar of pressure back. Let's give it another test. So, it would appear that this diameter is already too small for this engine, which I know it sounds weird because I didn't decrease the diameter by that much, but keep in mind that for the nozzle, what matters is the area, and the area scales with the square of the diameter. So for example, if I make the diameter half its size, the area actually shrinks by 4 times. But don't worry, because I have a cool experiment in mind. I mean, it's the entire point of this nozzle. What I'm gonna do is set the diameter to the biggest size, run it, and then adjust the diameter while it's running. I mean, sounds pretty cool to me. Someone might say that my adjustable nozzle worked perfectly, and that someone is me. But come on, I know I'm shamelessly bragging, but you don't see this every day. I mean, I was able to adjust the size of the nozzle while the rocket was running. That's pretty cool, right?
Also, it was a good learning experience because I realized something. When the nozzle was fully open, it ran smoothly, but not to its full potential. As I would close it, the exhaust became sharper and louder. But if I went too small, the engine would start pulsing with sharp bursts. That happens because as I decrease the diameter, the chamber pressure increases, and when it reaches a point where the chamber pressure is higher than the feed lines, the inlets, it pushes the propellants back, which is neither safe or good.
Yeah, this little guy has some design problems. So for starters, this is not a circle, it's an hexagon, which kind of looks cool, but is not great for performance. Otherwise, bees would excel at rocket nozzles, and the only thing that can make is honey. Useless. The other thing is, this is just a hole, and the nozzle is not supposed to be just a hole. It's supposed to have a converging cone and then a diverging section. I can't start to imagine how I would do the divergent section, but I think I have an idea for the cone.
Have you ever heard about something called an afterburner? It's a special part of a jet engine that heads more fuel after the main combustion. They normally come with this adjustable nozzle mechanism that uses moving blades to achieve varying cone sizes.
The problem is that afterburners use this complex mechanism to both slide and tilt the blades so you generate a different size cone, and at the scale I'm working with, it's not easy to pull that off. What do you say, Julius? You know a thing or two about blades?
ありがとうございます。
My idea is to keep this simple, is to use an 1/2 inch threaded connector and a 1/2 inch nut to achieve up and down translation. If I pair that with a slider and a truncated cone, I can attach blades to slide up and down. The only way to do this with flat blades is to stack them like fish scales, so they have room to move. The problem is that I'm still getting an hexagon. If instead of flat blades I use curved ones, I get better interlocking and a better nozzle shape, but whatever that shape is still not a circle. My best shot at getting a circle is with this. This is 0.1mm thick sheet steel. It's so thin that it's very flexible, so it might just force itself into shape.
Okay, so I tried to use my CNC machine to cut the blades, and look, it did a great job. It cut them very cleanly, which is really surprising because this machine normally can't cut anything tougher than brass, but I guess this is so thin that it was able to do it. The downside is that I probably ruined my engraving tool, but that's fine, I have more. I mean, sometimes you need more than one cutting tool to get the job done. Right, Julius?
Vaffanculo.
Oh, that is so smooth. I mean, there's still a little bit of friction here, but you know what? This is what I call a circle. I mean, at least on the inside. Outside, not so much. But you know, what matters is in the inside.
He's not wrong, you know. In fact, he's absolutely right. What matters is on the inside, and what's on the inside of those blades is a resin part that is really flammable, so I need to make it out of metal.
Nice. Hot.
Here it is, my nozzle in shining armor. Looks pretty cool, and as you can see, unlike my opinion on tomatoes, is rather flexible and adjustable. I was really surprised that the blaze didn't get obliterated by the pressure and high temperature. I mean, I know it's steel, but 0.1 millimeters? That is insane thin. I'm not gonna lie though, the blaze did get pretty oxidized after a few tests, but other than that, it worked pretty well. This is pretty neat. I can see myself using this in the future as a tool to design small rocket nozzles without math.
By the way, I have nothing against math, it's just that testing is more fun. Now, I've been thinking of a way of actually doing a full variable geometry rocket nozzle, and I think I came up with an interesting approach. So my idea is, instead of going with the Delaval design, which is hard to accomplish, I would go with the aerospike design, and somehow by translating the spike in and out, I would be able to control the entire geometry of the nozzle, you know? Convergent, throat, divergent, everything. I don't know. It sounds like a good idea in my head, but I think I'm gonna have to give it a little bit of time and thought. So in the meantime, thank you so much for watching, and remember, tomatoes are disgusting. See ya!